Greetings, my name is Martinez. I am a graduate student at Vanderbilt University, and I'll talk about how we have been predicting public transportation load to estimate the probability of social distancing violations on behalf of the research. Affordable public transportation is essential for thriving societies. Public transportation agencies try to maximize coverage and ridership, but COVID-19 has imposed them numerous challenges, which need to be addressed. Some of these challenges have negative consequences on vehicle capacities and also on driver availability. In Nashville, ridership dropped from 150,000 people to about 75,000 after the lockdown was declared. However, the change in ridership was lower for the low-income group, even during phase one of the lockdown. Our approach consists of three main tasks. First, we built a dataset using information from GTFS and automated passenger counters. Given that the collected data can be noisy, we consider and assess uncertainty by exploring different probability distributions. For the second task, we use our data to build machine learning models to predict board and alight counts for all the routes at their bus stops. These allow us to simulate board and alight counts for all the trips at any given bus stop. These values will be used as inputs for the occupancy models, and thus we will be able to model and predict occupancy of any given trip between two consecutive bus stops. Finally, accurate occupancy models will provide information to avoid crowding, improving passenger guidance. A bus route is an ordered set of scheduled trips that visit a sequence of predefined bus stops. The occupancy of a trip is the number of passengers, which depends on two random processes, boarding and alighting. If we assume that trip T visits a sequence of bus stops, we would be interested in modeling board and alight counts. Exploring our data set, we found that the mean and variance of these two variables increased from early in the morning until the afternoon. However, we also noticed over-dispersion and consistent zero counts over time. This suggests that a Poisson distribution is a sensible approach to model board and alight counts. Thus, we assume that the board and alight counts at S of I follow Poisson distributions whose parameters represent their average counts per unit of time. Also, we define two probability distributions, f sub e and f sub a, for board and alight counts. Then our goal is to learn the probability distributions of these two variables conditioned to a set of features that characterize a bus stop at any given time. Besides that, we want to model the occupancy of trip T at S of I as the sum of its previous occupancy plus its current board count minus its current alight count. Finally, we need to define a sensible unit of time for the parameters of the distributions. For example, this figure shows the board counts over time of a particular route and direction ID at a bus stop. Clearly, zero counts and mean board counts are consistent over time. However, the mean board counts have low variability. In contrast, the maximum board counts are highly variable but fluctuate around a consistent mean. Hence, if we consider weeks as time units, we would not be able to capture the variability of board counts. But if we constrain the unit of time from weeks to hours of the day, we get a different pattern. In this case, we can see that the mean and maximum board counts have a greater variability and even exhibit a daily cycle. To model boarding distributions, we group the data by stop ID, day of the week, and hour of the day. Then we propose multiple count-based models using features like time of day, month, and years coverage. We included Poisson negative binomial regressions. Also, zero-inflated models using Poisson negative binomial distributions for the values greater than 0. For example, in the case of a Poisson regression model, the mathematical form of the regression is as shown. In this figure, orange dots represent word count data. The red dots indicate their hourly average connected by a red dashed line. Then we predicted the board counts and their averages using the selected models. We repeated this process for all the routes and their bus stops. Then we model the allied counts. For this situation, we need to guarantee that the current allied count is less than or equal to the current occupancy. Therefore, we need to truncate the allied count distribution to avoid negative occupancies. Here, I is an indicator function, and the current occupancy is given by the difference of the cumulative board and allied counts. Our data includes 545 days of record. 80% of these days were used for training and 20% for testing the models. We averaged the MSEs of the models over all the bus stops and days of the weeks. Overall, the Poisson regression model had the lowest MSE. The following figure shows the accuracy of the Poisson regression model. At the top, the board count data, and at the bottom, the allied count data. The orange dots indicate the observed board and allied counts, and the red dots indicate their mean value connected by red dashed lines. The blue dots indicate the prediction of board and allied counts, which are connected by blue dashed lines. Clearly, these models are able to capture the daily fluctuations of these variables. Our current work focuses on building occupancy models considering the ordered sequence of bus stops and the arrival time difference of the trips. Also, we're trying to integrate real-time weather, traffic, and demographic data into our models. Besides that, we're trying to estimate ridership based on counterfeits. Thank you.